Welcome to the Learn While Sleeping podcast. Imagine you just woke up alone on Mars. The glass of your habitat trembles from the wind outside. Red dust rolls endlessly across the horizon. The sky is thin, pink, and quiet. The oxygen gauge on your wrist blinks. You're an astronaut, or perhaps maybe a survivor, standing on a world that looks like the Earth's ghost. Air outside can't be breathed. It's too thin, and there's almost no pressure at all. The sunlight looks bright but feels weak, scattered through an atmosphere made mostly of carbon dioxide. When you step outside without a suit, and the moisture in your lungs would boil instantly. Not because it's hot, but because the pressure is so low that water can't stay liquid. At nighttime, the temperature drops to about minus 80 degrees Celsius, cold enough to crack steel. And yet, Mars is the planet we talk about most when we talk about life. NASA keeps sending robots to Mars. Movies keep stranding humans there. We imagine greenhouses and domes and first colonies. So here's a question that starts everything. Could we actually survive on Mars? And could life ever survive anywhere else? That's what we're going to try and figure out together today. We're going to use real planetary science to answer two things. Number one, what makes a planet capable of life? And two, if those conditions appear somewhere else, could perhaps aliens, even microscopic ones, exist? By the end, we'll come back to Mars and see how it scores. But first, we need to know what the test even is. What does a living planet need? Let's start with something simple. Temperature. Every planet orbits a star, and that distance decides its warmth. You get too close to the planet, you get too close to the sun, and then, the oceans will boil. Too far away from the star, and then they freeze solid. Between these extremes sits this narrow band called the habitable zone, or the Goldilocks zone. It's not too hot and not too cold, just like the Goldilocks story. The porridge that's just right. Earth actually happens to live comfortably inside it, which is very rare. Venus itself is just a little closer to the sun, and that tiny distance change is what changed it into an inferno. Mars is a little farther away, and that tiny difference turned it into an icy desert. It's actually wild how small that margin is. Shift Earth's orbit by just a few percent either way, and life as we know it instantly collapses. But distance isn't the whole story. A planet also has to hold on to heat. That temperature on its atmosphere, the thin film of gas wrapped around it. Earth's atmosphere acts like insulation. It traps enough heat to keep us warm, but still lets energy escape so we don't cook. Venus actually went too far. Its thick atmosphere traps sunlight so well that its surface can melt lead. Mars went the opposite direction. Once again, as we discuss how cold it is, its atmosphere is actually so thin that it can't hold heat at all. Temperature then is a balancing act between sunlight and atmosphere. A planet needs just the right combination of distance and insulation to keep water liquid. Which brings us to the next rule on our checklist. A liquid solvent. If you actually stop and think about it, life itself, every form of life, it actually happens to be in liquid. Our blood, our cells, our oceans. Liquid gives molecules a place to move, meet, and react. It's the dance floor of chemistry, basically. And on Earth, that solvent is water. And water is kind of magic. It's sticky. Molecules grab onto each other but still move freely. It stays liquid over a wide range of temperatures. And then it floats when frozen, which keeps oceans alive even in ice ages. That one property, ice floating, this property is actually why fish survives winters. Like if ice sank, lakes would freeze solid from the bottom up, and life would never have left the ocean. So water's weirdness is not just convenient, it's actually essential. But what if another world doesn't have water? Could something else play that role? I mean, it's hard to actually imagine or conceptualize when we only know about water. Well, the answer is maybe. Saturn's moon, Titan, has lakes of liquid methane and ethane. Methane and ethane are types of gases in their liquid form. It's so cold there that methane actually behaves like water. It behaves just like how water does on Earth, in the way that it rains, they pool, and then they evaporate again. So if any form of life exists there, it would breathe chemicals instead of air, and then swim in complete liquid natural gas. It's a completely alien concept, but it's not impossible. What matters isn't what the liquid is, but that it's there, and that it's stable, flowing, and part of a cycle. Remember, we're used to the idea of what we live in, but different organisms evolved to handle different extremes. So far, we've got 2 items on our living planet checklist. We have a comfortable temperature range, okay? And we have a liquid solvent for chemistry. But those 2 alone don't make a world alive. Venus is hot and has clouds full of acid. Mars has ice and sometimes flowing brines. Neither are truly alive. So what exactly else is missing? Let's think about it. So we've got temperature and liquid covered. These are 2 boxes checked on our How to Make a Living Planet checklist. Now let's talk about something that most worlds actually completely mess up: the atmosphere. Think of it like the planet's outfit. You know, when you go outside and it's too cold or it's too hot, you want to have the right outfit for the temperature and the environment. So the planet needs the same thing. It can't just exist completely naked. Too thin of an atmosphere and it completely freezes. Too thick and then it suffocates. Earth wears a perfect hoodie, warm, breathable, and flexible. Venus is dressed in a permanent hazmat suit. Mars forgot to put anything on and has been shivering for 4 billion years. You see the problem here? An atmosphere, it does a few critical things. It holds pressure so liquids can exist. It traps just enough heat to keep things cozy, and it protects the surface from space junk and radiation. Without an atmosphere, your oceans boil away and your DNA gets deep fried. Like, radiation is what destroys DNA immediately. It completely denatures it. And without DNA, your cells are done. They just collapse. Here's the fun part. Every planet's air sounds like a custom smoothie recipe. Earth has its own blend, mostly nitrogen with a splash of oxygen, just right for lungs and forest fires. Venus went heavy on carbon dioxide and sulfuric acid foam. Mars has a thin carbon dioxide mist that's about as breathable as a vacuum-sealed Pringles can. Absolutely not ideal. This is why any talk of terraforming Mars basically means to give it a whole new atmosphere. It's the interplanetary version of changing your entire wardrobe and climate control system all at once. Next, let's talk about another thing. This is actually a big deal. We've talked about temperature, atmosphere, and all these things, but what does the planet actually run on? This thing is energy. Life actually runs on something called an energy gradient. So when we say gradient, we mean like it flows sort of between light versus dark, hot versus cold, full versus empty. It's not like constantly hot, constantly full, constantly light. Something else needs to flow from the high energy to the low energy, and life sneaks in to steal a bit of that ride. On Earth, most of that energy comes from the sun. Plants turn photons into food. They absorb these photons via photosynthesis from the sun, and then animals will end up eating these plants, and they absorb that energy, and then they'll metabolize it. Metabolizing is basically a bunch of reactions where they burn out that energy and absorb it, and the whole pyramid hums along like a kind of a food pyramid. Okay, so everything about life revolves around an energy input that's going to flow through all the living organisms. But there are also organisms deep under the sea that have never even seen sunlight, so we're probably thinking, where do they get their energy from? They actually live near what you call hydrothermal vents. These are really extreme environments, and they feed on chemical reactions from the planet's core. So basically, they're dining at the Earth's geothermal buffet. There is so much heat and so much extreme energy near the core that they can actually absorb on their own. So when we think about alien life, we don't just ask, oh, is it near a star? We ask, where's the energy coming from? Because even a dark, frozen world can glow with possibilities if it's warm inside, right? It's not all just about the sun or the star. That's why a moon like Europa, for example. Europa is a moon that revolves around Jupiter. And yeah, believe it or not, there are moons that revolve around other planets. We don't have the only one. This moon specifically, well, scientists are fascinated by it because it's covered in a crust of ice. And underneath that ice, there's a hidden ocean which is actually heated by Jupiter's gravity. There is so much heat energy underneath that the potential is clearly there for life. Scientists have been researching this like crazy because of that. It's the cosmic version of finding out that the creepy basement is actually a tropical spa. Here's another thing that Earth nailed: a magnetic field. It's invisible, silent, and the only reason we're not microwaved by solar wind. Inside Earth's core, molten iron moves like giant dynamo, creating magnetic lines that stretch into space. Okay, so this iron, it deflects charged particles from the sun, our own personal force field. Every time you see the northern lights, that's actually our magnetic field in action, turning deadly radiation into art. Okay, because if we didn't have this magnetic field, we would be so doomed, because all the radiation that comes instantly destroys all the DNA that exists in our body. Mars actually used to have one, and then its core ended up cooling, so the magnetic field completely collapsed, and the solar wind, which is basically fancy words for all the hydrogen ions that come from the sun, they slowly sandblasted its atmosphere away. That's why today it's bare and dry. It's a little like forgetting to renew your antivirus subscription and then watching your system melt down in real time. So, to add another checkbox to our list, we have a magnetic shield which keeps our Earth intact. We actually need this as like an antivirus system to keep humanity alive. What else does a planet need for life to exist? Well, a planet needs to move. Geology might sound boring, but it's the difference between a world that breathes and one that suffocates. Earth's crust is a restless patchwork of plates sliding back and forth and all around over molten rock. The Earth's plates, they collide, dive, and push mountains into the sky. In volcanoes, they'll belch out gases that rebuild the atmosphere. Rain wears down rocks and carries nutrients back to the sea. This loop, it's kind of like planetary metabolism. If you stop that motion, you end up getting a stagnant world. Venus, for example, it barely moves. Its surface resets every few 100 million years in one catastrophic resurfacing. Mars, it froze from the inside out. Earth, we still have this movement inside our plates and our crust, so what that means is that we actually have kind of like a living movement under the Earth's crust, which is actually essential for life. We're still dancing in a way. So think of plate tectonics as the universe's recycling program. This program keeps carbon balanced, it refreshes our minerals, and gives us earthquakes, volcanoes, and entire continents. Sometimes it can be annoying, for sure. But is it necessary? Absolutely. By now, our recipe for a habitable world is starting to look pretty specific. We have temperature, liquid, atmosphere, energy, magnetism, movement. And yet, if you look at the movie The Martian, based on the book by Andy Weir, it's really interesting. It actually shows us a human that's trying to cheat that system. How would they cheat a system like this? The character Mark Watney, played by Matt Damon, doesn't have a magnetosphere. They don't have a breathable atmosphere. They don't have liquid water on top. But somehow he makes it work. He keeps improvising one step at a time. When he says, I'm gonna science the heck out of this, he's really saying, I'm gonna recreate every missing ingredient for life by hand. Now just imagine if you were this guy and you traveled to Mars and you were stuck there. Okay, it is science fiction. Like, the likelihood of this actually occurring is pretty minimal, but it's thinking that if you understood how life can exist on another planet and you had all the resources in the world and maybe it's fiction, you wanted to try and make this thing work, how would you do it? Well, in a way, that's why The Martian isn't just a survival story. It's actually a tutorial on planetary engineering. It shows us what happens when a clever human tries to out-engineer evolution. We're going to test that in a bit. But first, there's one final ingredient that our list needs. One that ties all the others together. This final thing is a cycle. Because a living planet doesn't just have water or air. It recycles them endlessly. And that's where we're going to pick up now. So far, we've built the skeleton of a living world. When I say skeleton, I'm basically saying, like, we have all the right things. We have the right tools. It has the right temperature, a liquid solvent, an atmosphere to hold it, an energy source to power it, a magnetic shield to protect it, and moving geology to recycle its surface. Okay, seems like we're almost there. So what exactly are we missing? Here's the problem that most science fiction tends to skip. Life doesn't just need ingredients, it needs a system. A planet can't just have water. It needs a water cycle, something that constantly redistributes it, cleans it, and then makes it available again. Now, when we look at Earth, Earth has this beautifully, almost rudely self-sustaining loop. The sun heats our oceans, okay? And then water evaporates. When water evaporates, it ends up forming clouds above, and the clouds will end up moving, and then rain will fall. Okay, and then when rain falls, what happens next? We have rivers that end up flowing due to the rainfall, and then our oceans will refill. And then we can rinse and repeat this process for 4 billion years. That one loop ends up doing everything for us. It regulates climate, it grows forests, it dissolves minerals, shapes continents, and then it turns deserts into grasslands, and then back and forth again. It's like the planet has a built-in washing machine, heater, air purifier, and transportation system, which all runs on sunlight. Whenever you look at a dam, for example, like Niagara Falls, we get a lot of our electricity and energy from hydro energy, right? These things are not so far-fetched away from how our Earth sustains its own climate energy by itself. Now imagine Earth without a water cycle, okay? The oceans, they would just stagnate. The land ends up drying out. Weather just stops. I mean, why would weather stop? Well, remember, when the water heats up, all of that water needs to evaporate and then form clouds for rainfall. So if the oceans stagnate and there's no evaporation, weather stops. Life itself just completely collapses into small pockets and then eventually just disappears. This is the major difference between a planet with water and a planet with a living hydrosphere, which is what we have. This is why we get excited when we see signs of water on Mars. And then immediately we get disappointed when we remember that it's frozen, locked in soil, or evaporates the second it melts. It's not enough for us to just have water on Mars. We need to see signs of Mars having an actual water cycle. Right now, what we're seeing is mostly leftovers. So if you zoom out, this same pattern shows up in every part of a habitable planet. So we have the carbon cycle, okay? Not just water cycle, we have a carbon cycle. This cycle controls greenhouse gases and temperature. Then we have a nitrogen cycle, which will feed the plants and basically therefore everything else. Also keep in mind the nitrogen cycle was actually discovered fairly recently by Fritz Haber, a German scientist. And this is one of the major reasons why agriculture has boomed in the last 100 years. Okay, then we have the rock cycle. The rock cycle, it basically creates continents, mountains, and ocean floors. It regulates these things. Life has cycles that are basically almost alive. It doesn't just need resources, it needs this circulation. You wouldn't survive if all your blood froze in one arm, even if you technically had blood. Just having blood is not enough. You need them to actually regulate. So planets are the same way. You need to look at planet in a living sense, almost like it's a whole organism on its own. This is why the moment a world loses its cycles, when water stops flowing, air stops refreshing, and rocks stop moving, well, the planet doesn't die overnight, but it stops being alive in the planetary sense. It basically becomes like a fossil. That's kind of what we're looking at when we look at Mars. Now here's the philosophical twist. A living planet behaves like a giant organism. Like I said earlier, it eats energy, exhales heat, breaks down old material, renews itself, and then protects its surface. This is why some scientists call Earth a self-regulating system, even though it has no brain. It's not really intelligent, it's just interactive. It's not conscious, but it is balanced. But balance is fragile. If you remove one loop here, the whole system just drifts. That's why Venus lost its water and entered runaway greenhouse mode. Mars lost its magnetosphere, and then its atmosphere, then its liquid water. Both had the potential, but both failed the maintenance phase. This is the actual truth behind all of this. Life doesn't just need a place to start, it needs a place that stays habitable long enough to evolve. I mean, it can be born in chaos, but in the end, life only thrives in cycles. So this is kind of like a blueprint that we have now about the species neutral recipe for habitability. And it works for bacteria, plants, the hypothetical alien goo or floating gas creatures in Jupiter's clouds. And now we can actually test it We can run a little thought experiment right now and see if we can figure out if life can actually exist. We're going to take this checklist and run it through the Martian scenario. Not the movie first, the real Mars itself. We're going to try and score the planet the same way you'd grade an apartment listing. We're going to run this little checklist. We're going to ask it, like, does it have water? Does it have an atmosphere? Etc., etc. And let's see whether or not Mars gets a 5-star review. But, this is what makes the movie interesting. It's not about living on a habitable world. It's about watching a human fake the missing parts of one. And that's where we go next. Okay, so now let's say we have our checklist in our hands and we're walking back to that red desert, Mars. It's like our neighbor planet and maybe someday our future address. It looks close on a telescope, but in reality, this is the cosmic equivalent of moving from a warm apartment into a half-collapsed shed with no heat, no plumbing, and constant sandstorms. Doesn't sound exciting, but this is the mystery about colonizing a new place. So let's grade it. First, let's look at the temperature. The average day in Mars is about negative 60 degrees Celsius. And at nighttime, it's about negative 80 degrees Celsius or worse. The summer noon near the equator might barely reach a comfortable jacket day. And then when you plunge to the Antarctic cold before midnight. Mars technically sits just outside the sun's habitable zone, so it's not way too far. But because its atmosphere is so thin, it just can't hold any warmth. So what's our verdict? Well, it has a failing grade for comfort. It's definitely not too comfortable. But it does have a passing grade for, it could maybe work if you bring space heaters and optimism. So there's a bit of a hypothetical there. But realistically, it's not really the best for temperature. Okay, and then let's look at atmosphere. About 1% of Earth's pressure, almost pure carbon dioxide. You could step outside for a few seconds, just long enough to say this was a mistake, before your blood immediately begins to fizz. That's crazy. Literally, your blood starts to fizz. Every Mars story has wrestled with this concept. The Martian by Andy Weir, it gives Watney his hermetically sealed greenhouse, and that's how he manages the atmosphere. The movie Total Recall, it imagines entire domed cities under glass, living in Mars. The TV show The Expanse, again another science fiction, it assumes that future technology is so good that Martians basically stroll in half-pressurized corridors and no one cares. Again, these are all thought experiments in science fiction. So far, reality sits closer with The Martian. The idea of everything being airtight, it does give us the idea that there would be zero margin for error. Okay, now we're going to talk about water. Mars once had rivers and deltas. Okay, it's not like it always looked the way it does right now. NASA's rovers actually keep finding dried lake beds, and in 2023, radar data hinted at briny underground pockets. So the water on Mars does exist, but right now it's locked in ice or salt. That's why we kind of look at this planet as if it's a fossil. In The Martian, Watney pulls hydrogen from rocket fuel, and then he burns it with oxygen to make water vapor, nearly blowing himself up. What does that sound familiar to? Kind of like our water cycle, right? When the heated up water from our oceans ends up evaporating and creating clouds and yada yada, we have a whole cycle, right? So he's using hydrogen from rocket fuel to burn that with oxygen and then make his own water vapor. This is real chemistry. It's also why astronauts joke that nothing on Mars is truly safe until it's been explored at least once. Then we can look at energy. In terms of sunlight, there's only about half as strong sunlight as on Earth. We have found that solar panels can work, but the problem with them is that dust storms can dim the planet for weeks. In Andy Weir's novel, he solved this conundrum with basically a backup nuclear generator, or what he called the RTG. This backup nuclear generator, it's what NASA uses on probes, like, for example, the Curiosity and Perseverance. These aren't just like buzzwords, these are the names of their probes. And historically, that's pure engineering truth. The first real power source on Mars will probably be small reactors, not sunlight. Because we can't just rely on sunlight when there's dust storms happening and blocking it up for a few weeks. So, in theory, this can work, but we're gonna need to engineer our own nuclear power source. Okay, so after energy, there's a last thing, which is the magnetic field and radiation. And remember how we said how Mars completely lost its magnetosphere. Mars did once have a molten core like Earth's, which was spinning up a magnetic shield. But then what happened is it ended up cooling, and the solar wind completely stripped away its air. Today, cosmic rays hit the surface unfiltered. So what this means is that real astronauts would have to live underground or under meters of waters, or like in sci-fi, the show The Expanse, it completely sidesteps this with futuristic radiation meds. Star Trek, for example, it just waves a deflector field. But for us, this is a major nope. It's not gonna happen likely anytime soon that we'll figure out some kind of way to bypass this. It's actually a big deal. In terms of geology, there is virtually no tectonic activity at all in Mars. There are no volcanoes. Volcanoes have been extinct for millions of years. And without this geological movement, there's no recycling of carbon or renewal of atmosphere. And what it means is that the planet is geologically asleep. When you compare that to Earth, which is still churning and still alive, you could say that Mars is like our older sibling that moved out early, stopped paying its heating bill, and just froze solid. So for our final moving in score, let's look at those categories. So for temperature, it's barely survivable. For atmosphere, it's too thin and toxic. For liquid water, it's rare and briny. For energy, it's limited but possibly workable if we have some of our own ingenuity. And for the magnetosphere, it's completely gone. Geology, dormant. Mars is almost there. I know it seems like it barely fits any of the criteria, but it is the universe's equivalent of some assembly required. And that's why The Martian hits so hard. It's not complete fantasy. This movie is kind of an instruction manual for cheating the rules of habitability. The character Watney, he recreates Earth in miniature, a warm, pressurized bubble, an internal water cycle, plant life, and energy from sunlight, even a bit of atmospheric chemistry. So he's kind of building this habitable center from scratch, where the planet can't reach out to support him. A little history about this. We've been chasing that dream for decades. The first successful landing was the Viking 1 in 1976, which looked for microbial life and found ambiguous chemistry that still sparks arguments today. In 1996, a meteorite from Mars was found in Antarctica and showed structures some thought were fossil bacteria. NASA announced, "We may not be alone." And then the scientific community collectively said, maybe don't get too excited just yet. But still, those moments built the mythology of Mars. Every rover, like the Spirit, Opportunity, Curiosity, and Perseverance, they've all added a footnote to the same story that we're building, which is that this world was once alive with rivers, maybe even oceans. So the question is whether anything microscopic ever managed to hang on. So, could life exist on a planet like Mars? Not surface life as we know it, but maybe deep below, where salt and pressure keep water liquid. If we ever manage to dig down and find even one dormant microbe, this is going to rewrite biology textbooks. It would prove life doesn't need a paradise, but just persistence. So next we're going to stop a bit farther out beyond Mars, to worlds even stranger. Icy moons, methane seas, and exoplanets that make science fiction look cautious. Because if Mars is almost habitable, those places might show us how many versions of almost the universe allows. So we're still looking at what makes a planet capable of holding life. And if Mars is just a maybe, well then the outer solar system is a cosmic plot twist. Because we've been thinking about our galaxy this whole time. And yes, there are planets that are in habitable and very uninhabitable zones, have bad or good temperature, but we're not limited to these several planets. Right now we are, we can't fly very far, but never say never. Technology may develop in such a way that at some point we can travel beyond our galaxy. And if that's the case, and just because you think you know what life needs, like warmth, sunlight, and air, the universe ends up saying, hold my comet. So let's start with Europa, which is one of Jupiter's moons. Okay, and at first glance, it does look dead. It's a smooth, icy shell covered in scars and cracks. But beneath that ice, scientists actually believe that there's a vast ocean. And in this ocean, there's more water than all of Earth's water combined. It stays liquid, not because of sunlight, but because of Jupiter's gravity, which kneads Europa like dough, heating its core from the inside. And remember, as we discussed earlier, it doesn't matter where that energy comes from necessarily. It doesn't have to be from a star or from the sun. So that constant flexing called tidal heating, it could power hydrothermal vents at the seafloor. The same kind of hydrothermal vents that host life on Earth's abyssal plains. If this is true, then Europa isn't a frozen wasteland. It's an inverted ocean world, with its ice mountains on top, and maybe alien shrimp below. NASA's Europa Clipper mission, which is actually launching soon, will fly by dozens of times, sniffing for plumes of water vapor spraying through cracks. If it finds organic molecules, like amino acids, maybe methane, that's biology's version of I was here graffiti. And to be very honest, I think the possibility of life existing here is pretty high. A good example is if you look at Arthur C. Clarke's 2010 Odyssey 2, it actually warned, all these worlds are yours except Europa. Attempt no landing there. This is the perfect line, because even he imagined that under those ice fields, something might be swimming, waiting for us to leave it alone. Our next stop is Titan, Saturn's largest moon. If Europa is cold ocean, well then Titan is cold chemistry. It's the only other place in the solar system with stable liquids on its surface. Not water, but methane and ethane. There are rivers, lakes, and even seasonable rain made of liquid natural gas. It sounds like a science fair disaster, but to astrobiologists it's thrilling, because methane could play the same role that water does for us. It is a solvent where weird carbon chemistry might flourish. Titan also has weather, which is orange smog, wind-sculpted dunes, and lightning storms. It's like Earth seen through an Instagram filter for nightmares. And yet, NASA's Dragonfly Dome, which is, yes, an actual rotorcraft, it is set to explore later this decade. The Dragonfly drone, it's interesting by the name. The craft actually is rotary, so it does resemble a dragonfly in a way. Also kind of resembles the vehicle in Dune. There's a spacecraft that has that similar dragonfly design. This will hop between dunes, sample organic goo, and then test whether pre-life chemistry could work in a world that's colder than Antarctica's soul. In fiction, Titan has shown up everywhere. If you look at the finale of Interstellar, in this movie, it echoes its methane seas. The Expanse, it uses its atmosphere as a setting for shady business and exile. And then in the sci-fi horror movie Alien, by Ridley Scott, the derelict spacecraft's moon, LV-426, it borrows heavily from Titan's foggy aesthetic. We like to keep revisiting it because it's proof that habitable doesn't always mean comfortable. And then there's Enceladus, a smaller moon of Saturn that shoots water geysers hundreds of kilometers into space. Those plumes contain salt, organic molecules, and maybe tiny ice grains formed around warm vents. Cassini actually flew through one. It was the first unintentional taste test of another ocean world. If microbes exist there, they're literally venting into space, like free samples for passing spacecraft. somewhere, a NASA engineer still brags that we've snorted alien ocean spray. Probably not on the mission patch though. What these worlds show us is that the universe is more creative than our definitions. We used to think that life needed water and, surface water, and it needed sunlight. Now we know that these are very strict criteria. It might be able to hide in darkness or under ice or even in chemical lakes. We're realizing that the rules of biology were just local laws. They're not cosmic ones. So now if you jump back even farther past Saturn's rings, even beyond Neptune's blue storm, into the black void, there are planets orbiting other stars, which are called exoplanets. And we have these exoplanets by the thousands. Some are like super Earths, with rocky and slightly bigger environments than ours. Some are mini Neptunes, which are gassy and strange. And a few of these exoplanets actually sit right in their star's Goldilocks zone, just like how our Earth does, with just the right warmth for liquid oceans. When the Kepler Space Telescope started finding them, the numbers blew our minds. There might be billions of potentially habitable worlds in our galaxy alone. Billions. Suddenly the question wasn't, are we alone? It was more like, why haven't we heard anyone else yet? Just basically, that's the famous Fermi paradox. Scientists has actually toyed with that puzzle for decades. Contact imagined radio telescopes catching a cosmic phone call. The video game Mass Effect built a whole universe around the idea that civilizations rise, fall, and leave ruins for the next ones. Right? Reality so far, we've had just complete silence. But silence isn't evidence for emptiness. It's just that the universe is on mute, and we're trying to figure out how to learn to listen better. Every new telescope sharpens that search. The James Webb Space Telescope is already reading the atmospheres of distant exoplanets, looking for biosignatures, like gases that shouldn't exist together, unless something else alive is constantly making them. Oxygen plus methane, for example. Or maybe something totally new that we wouldn't even recognize yet. When Webb or its successors spot that first weird chemical fingerprint, it will be the biggest discovery in history. This is going to be proof that life's recipe actually works more than once. So far we've looked outwards, from Mars to Europa to Titan to the farthest exoplanets we can barely even see with the human eye. Next, we'll flip the question inwards. If the universe is that generous with potential, well, what made Earth's version of life so rare? And just how fragile is our own habitability? Because in every sci-fi story, like Interstellar, The Martian, Avatar, there's a little subtext. And this subtext is the same. When we dream of other worlds, we're basically trying to understand our own better. If you think about it, we kind of just took a tour around the cosmic neighborhood. We looked at Mars with its empty skies, Europa's buried ocean, Titan's methane dreams, and 1,000 invisible worlds circling distant suns. So now when we circle back home to the only planet that we know works, from orbit, Earth happens to glow soft blue and white, like a fragile ornament floating in darkness. Astronauts say that the first thing they notice isn't how small it looks, but how alive it looks. If you notice from outer space, Earth, it actually shows movement. You see clouds swirling, oceans pulsing, lightning flashes like neurons firing across the brain. Compared to everything else there, Earth actually kind of looks awake. That might be the real definition of habitability. Not just a world that can host life, but one that's learned to keep itself balanced. 4 billion years of feedback loops, rain cooling volcanoes, plants exhaling oxygen, and oceans absorbing heat, mountains recycling minerals. This is not like magic, it's actually just the Earth maintaining itself. So, when we call Earth a miracle, we're really admitting we don't yet understand the odds. It's kind of like a miracle that isn't a miracle. I mean, maybe the universe makes living planets all the time, and we just haven't spotted the others yet. Maybe we just hit the cosmic jackpot and it really is only us. Either way, it's easy to forget how narrow the margins are. A few degrees hotter and we would be Venus. A weaker magnetic field and our air would vanish like Mars. If we had a slightly dimmer sun, then the oceans would lock under ice. Every scientific film, or every sci-fi film, where humans flee a dying Earth, like Interstellar, Wall-E, The 100, you can take your pick. They're all built on this anxiety. Like, what if our perfect settings drift? We have had this anxiety for a while. What if the system that raised us finally changes the locks? So, this is where a big question lands. We're going to talk about the Fermi paradox and the Great Silence. We have this big question. If the universe is filled with billions of habitable worlds, where is everyone? That's the Fermi paradox. It's a fancy name for a simple frustration. Statistically, life should be common. But yet, we look out the sky and we look into space and it's completely quiet. Some scientists say we're early. Others think civilizations burn out fast, like cosmic mayflies. Or maybe life hides under ice or deep underground, never learning to shout across the stars. Pop culture has an answer for this that it loves to fill this science with. Generally, it always likes to use this idea of ancient precursors, like in Mass Effect, for example. Or you have parasitic invaders, like in The Thing. We have friendly diplomats in Star Trek, and we have nightmares in Alien. But in the real universe, silence is just data that we haven't decoded yet. So there's no deep explanation there's no deliberate reason why there's silence. Maybe it's not empty out there, but maybe it is just private. What searching teaches us is that even if we never find aliens, the search itself already matters. Now, this is something that's pretty interesting. I myself, from a young age, always wondered, why do we consistently put in so much effort to look in these other planets and other places for potential life if it seems so difficult to even fulfill these criteria? There's a good reason. It forces us to look at Earth in the way that we look at Mars. I mean, think about it. We're looking at Earth analytically, carefully, and almost lovingly. This is reminding us that habitability isn't permanent. It's earned generation by generation. Every telescope we launch, every probe we land, is a mirror turned back on ourselves. We study other worlds to understand the contract that keeps ours alive. And that contract is simple. Keep the cycles running. Don't break the balance. We look at SpaceX, for example. Humanity has a huge push to finding life on Mars or planning our own colonization of another planet, which is definitely not an endeavor that's in vain. But it makes you think, why not also put in that effort to maintain what we already have, right? And because we already know what happens when a planet loses its shield, its water, and its motion, we've seen the corpses. Mars, Venus, and countless exoplanets are scorched and frozen. They're basically like planetary corpses just right in front of us. Because life did exist once, or potentially did. Earth is alive because it still breathes. Our job is to make sure that Earth keeps breathing. So there is the philosophy of habitability. And maybe that's the real answer to what makes a planet alive. This is not just physics, it's temperature and magnetism and plate tectonics and continuity. The ability to adapt, to repair, to start over when things go wrong. A living planet, like a living species, must keep rewriting its own instructions. In The Martian, the character survives by doing exactly that. He adapts faster than the environment can kill him. Humanity's version of that challenge is planetary scale. We're the species in the habitat, surrounded by red dust and finite supplies, trying to science the heck out of staying alive. So, as a closing thought, somewhere, maybe right now, a small creature under Europa's ice is doing the same. Eating, dividing, enduring, with no idea that far away another world is wondering if it exists. Maybe that's how the universe works. Countless tiny experiments in survival, each unaware of the others. Each proving that life doesn't wait for comfort, it just waits for a chance. And this is the end of our episode on the possibility of the Martian being real and the possibility of life existing on a planet. Thank you for listening. If you enjoyed, please subscribe to the podcast on Apple Podcasts or Spotify, or on YouTube if this is where you're listening.